Now we are ready for antiderivatives. So, before we get into the meat of it, let's talk about like how they're helpful. In physics, I have this on your worksheet. It says, suppose the blank of a particle is known and you want to find its blank. And so what we're going to do is say, suppose the velocity is what goes in the first blank. Suppose the velocity of a particle is known and you want to find its position. So velocity is what goes in the first blank. And you want to find the position of the particle. And then I have another example we can look at in engineering. Suppose the blank water is leaking from a tank and you want to know the blank over a certain period of time. What should go in that is the rate at which water is leaking from a tank, and you want to know the amount leaked over a certain period of time. Or in biology, suppose that you know the blank, and this is again, it's the rate at which a population is growing, and you want to know the population at a future time. If you had any one of these situations, and this is what you know right here, and this is what you want to know right here, you have the velocity, which is the derivative of position. You have the rate at which something is leaking, or the change in the volume per time, and you want to know the amount leaked, or the volume that has drained out. Or the rate at which a population is changing, dP, dt, and what you'd like to know is the population over some time. So in all of these cases, what you know is the derivative, and what you want to know is the function that you got the derivative from, which is the antiderivative. So we're doing an inverse process here. So in this introduction to antiderivatives, we're just kind of getting our head around what function could I find that would give me this as a derivative. That's kind of how you want to think about an antiderivative. And so there's a definition there. It says a function f is an antiderivative of little f on an interval I if the derivative of capital F is little f. So again, you want to think of the capital F, the antiderivative. It's the function whose derivative is little f of x. The function whose derivative is little f of x. So let us consider a function that we are pretty familiar with. We've seen this for much of our math life. Let's consider that we've got this. This is a little bitty parabola, okay? So let's just see here. What function could I find, could I take the derivative of and get this? What could I take the derivative of and get this? Well, you know how when you take it's a power function, okay? So we think, okay, it's a power function, and so you would subtract the power, right? When you take a derivative, you move the one in front. So we would move the number in front, and then we would reduce the power. So we're going to do the opposite. We would have to have a power bigger than 2. We'd have to have a power of 3, right? And then we'd have to have something that would multiply this by that would give us a 1, because you always put the 3 in front. So we would have to divide it by 3 to get that. So let's give this a shot. Let's see, would this work? Let's see. If I take the derivative of this function, what would I do? I'd have this 1/3, and then I would take the 3 in front, right? And then I would take x, and I would raise it to the 3 minus 1, or the 2 power. So I find that f prime of x is 1x squared. So, okay, yeah, that works. This is one function that I could find whose derivative is this. This is an antiderivative of this. Are there more? Are there more? Let's just see. What if I took the derivative of this? what if I say f2 of x, let's say, what if it's 1/3 x cubed plus 6? Let's take the derivative of this. So to take the derivative of this, we throw the 3 in the front. 3 times 1/3 is 1. X to the 3 minus 1 is 2. And the derivative of 6 is 0. Oh, so when we take the derivative of this, f prime of x, we get x squared again. So that is another one we could find. Are there more? I think you're going to see that, yes, there are more. There's infinitely many more. We could just tack on a constant here and we get this derivative because the derivative of a constant is 0. So let's try this one. X cubed minus 1005. What's going to happen here? Well, the derivative of this, f prime, is going to be x squared plus 0, right? So this one does it. So this is what we've come across. This is called the most general antiderivative. It covers all of our bases. So if we find this antiderivative, but we just tack on this little constant right here, then we're covered. We have found all of the antiderivatives. So what they refer to this is as, and you can see in your textbook, there's a nice little picture. And you know from, remember horizontal shifts and vertical shifts of functions? When you just tack a number on at the end, you add a number, that's a vertical shift. What this is, it is a family of curves that all are off by this little vertical shift. So the cubic function, let's just pretend like this is x, this is maybe x cubed. What you get is like a family of functions that are off by a little horizontal shift. That's what this plus c. If you add 6 or subtract 2, you get a whole family of curves is what you get when you take an antiderivative. So that's a point that we want to make sure we understand. Okay, so now what we're going to do is we're going to practice coming up with some antiderivatives. So let's look at example 1, which has all these. I just gave us 3 to look at. We looked at x squared, and so we got through that one by saying, okay, what function could I take the derivative of and get that? Okay, what function could I take the derivative of and get that? Keep thinking that. And in example 1, we have f of x is the sine of x. Here's example 1. If f of x is the sine of x, what function could I take the derivative of and get the sine of x? Do we know one? Well, we know one that's kind of close. Cosine and sine are related to each other. If you take the derivative of cosine, what do you get? You get negative sine. So if I want to take the derivative of something and get positive sine, I just have to tack a little negative on there. Negative the cosine of x. Let's see, would this work? If I take the derivative of this, I would get negative sine of x, which is sine of x. Oh, cool. So that worked. So what would the antiderivative be? Negative cosine of x. And the most general antiderivative would be where you add that little constant on there. Let's look at B. Can we find an antiderivative for this one, 1 over x? Okay, you have to ask yourself, remember, ask yourself, what function could I find who has this as a derivative? And so this happens when you have a natural log involved. And so what could I take the derivative of and get 1 over x? Natural log. So the antiderivative is going to be the natural log of x. Okay, and if you want it to be the most general, then you tack on this constant, and that covers every function you could find that would give this derivative. Let's look at C. C is x to the n. X to the n. This is our power function, and this is, note, when n is not negative 1. Well, what happens when n is negative 1? Well, that's this special case, this natural log function. So that's not what we're talking about. We're talking about every other power function. And we already know this one because that's what we did a second ago when we looked at x squared. How did we get its antiderivative? Well, we added a power. We went x cubed, 2 plus 1, and then we divided it by 2 plus 1. So the antiderivative for any power function, so if this is our little f, then our antiderivative is going to be x raised to the n plus 1 divided by n plus 1. That's what the antiderivative will be. And then if you want it to be the most general case, then you tack on that little plus c. Now, what are we going to do? We're just going to practice, see if we can come up with a few, and then we're going to practice getting good at it. Okay, here we go. K, this is what I want you to put in your little chart. The function is k, this function is x to the n, where n is not negative 1. This is 1 over x. This is e to the x. This is the sine of x, and this is the cosine of x. Okay, so this should be pretty easy because we just thought through this, but I'm going to try to leave this on the board when we go through our examples. What could I take the derivative of and just get k? K times x. And then if I want the most general case, I'll say plus c. What could I take the derivative of and get x to the n? X to the n plus 1 divided by n plus 1. So sometimes they write it like this. 1 over x n plus 1 times x to the n plus 1. What could I take the derivative of? And if you want the most general case, you add the plus c. What could I take the derivative of and get 1 over x? It's going to be the natural log of x. And so I'm going to put, as you will see in the book, absolute values over x because we can only take the log of a positive number. So that is, that's what we need to do in case x is negative. What can we take the derivative of and get e to the x? Well, we know this one really well. It's e to the x. So that's it. What can you take the derivative of and come up with sine? There isn't one, but we can adjust that with a constant negative cosine of x plus c. What can you take the derivative of and get cosine? There is one that we don't have to adjust, and that is just regular old the sine of x plus c. Now, I want you to take note of something because this is so awesome. Every time you take an antiderivative, you can check to see if you got it right by just taking the derivative. You should get this back. So when we're doing these problems, you can always check your work. Just take the derivative, and you should get the original back, and you'll know you did it correctly. So let us go ahead and do some examples, and we will get really, really good at this. So example 2 goes like this. It says find all the functions of g, and when they say find all the functions, what they're saying to you is the family of functions plus c. You must put on that plus c. Find the family of functions for g whose derivative is this, where g prime is this. So they gave me a derivative. They want me to go backwards and find the function that gave me that derivative. And this is what it is. It says g prime of x, this is example 2. G prime of x is equal to 5 cosine of x plus 4x squared plus 2 square root of x divided by x. And so just like we were learning how to take derivatives, now that we're learning how to take antiderivatives, we don't know how to take everything in the world. We know a few rules. So far, these are the only rules we know. So we need to sometimes manipulate our function correctly, algebraically, legally, until we can get it in a form that we can take the antiderivative of. So let's see. What I'm going to do is rewrite this. This is a polynomial divided by a monomial. Well, this isn't really a polynomial because that's square root, but I'm going to divide this x into each of these terms. So I'm just working with my g prime. This is 5 cosine of x plus 4x plus 2. This is really x to the 1/2, right? And this is x to the 1, but when it crosses the fraction bar, it becomes a negative 1, so this will be 2x to the negative 1/2. The power rule is so awesome. As long as n is not negative 1, it doesn't matter if it's a fraction or square root or something, this rule applies. So we can use power rule here, and cosine, we have figured that out. So I'm going to put the 1 on there for help us figure this out. G of x, 5 is a constant. He's okay. He's just going to hang out right there. He doesn't affect anything. We look at the cosine of x. what function could you take the derivative to get cosine? And so we know that that is sine. So 5 times the sine of x plus 4 times x to the 1. What we would do is say 4x to the 1 plus 1, 2 divided by 2. That is the power rule, plus 2x to the negative 1/2 plus 1, or 1/2 divided by 1/2, and then plus some constant c. We can clean this up. G of x. Now, notice I'm not using capital G of x because they changed the notation. They said G prime of x, which means the derivative. So now I don't have that prime, so that means this is the antiderivative. So watch the notation, it changes some. This is the antiderivative, 5 sine of x plus 2x squared. 2 divided by 1/2 is a 4 square root of x plus c. This is the antiderivative for example 2. Here's example 3. Goes like this. Find f prime of x. Now find f of x if f prime of x is equal to e to the x plus 20 times the sine of x. And they gave us what's called an initial condition. And so that means we don't have to leave our final function in terms of plus c because we can go plug in a value and figure that out. So what I'm going to do is pause the video here after this one, and I'm going to pause the video here because I think y'all need a little break so you can look at that, and then we'll come back and tackle this one.